Hello guys, today we will deal with an example in which we will compute the mixed kind partial derivative of function of two variable, and we observe that in this example the mixed kind derivative of function of two variable are not always equal at the given point. So the example is, we have given that we have given a function of two variable fxy is equal to, this is xy, x square minus y square whole upon x square plus y square, when xy is not equal to 0 and it is equal to 0 when xy is equal to 0. Now we will compute the partial derivative of f with respect to x and y at a point 0, 0 and partial derivative of f with respect to y and x at point 0, 0. So we have to compute these two values. So as we know that the partial derivative of fxy, we can write this like del upon del y of f of x at point 0, 0, and this will be equal to limit k tends to 0, because we have to differentiate it partially with respect to y. In case of y, we take variable k and we have to partially differentiate the function f of x at which point? At 0, 0. So we will use here 0, 0 plus k, that is k minus fx 0, 0 whole upon k. So compute this f of x at point 0, 0. This is at point 0, 0. This is equal to, we need these two values. Number first, fx at point 0, k and fx at point 0, 0. And we know that the partial derivative of f, and we write it as f of x at point 0, 0 is calculated by this formula, taking limit s tends to 0, because we are differentiating it with respect to x. The function f0 plus h 0 minus f0, 0 upon h. So after simplifying this, we get limit s tends to 0 f h 0 minus f0, 0 upon h. Here we can see that the value of function when x, y both are equal to 0, the value is 0. So in place of this, we will use 0. And in place of x, we will use h. And in place of y, we will put 0 in this function. So in place of x, we will use h, and in place of y, we will use 0 in this function. So it become, because if we put y is equal to 0 here, so it give us 0 again, and 0 minus 0 upon h, this is equal to 0. So that means the partial derivative of f with respect to x at a point 0, 0 is equal to 0. Similarly, we can find fx at point h comma 0 comma k, and this will be equal to limit h tends to 0 f 0 plus h is h k minus f 0 comma k upon h. Now put in place of x we put h, and in place of y we will use k. Limit h tends to 0, we get h into k into h square minus k square whole upon h square plus k square, and f0 comma k is 0 upon h. From here we can cancel out h by h, and after taking h tends to 0, this becomes 0. In numerator we get minus k to the power 3, and in denominator we get k square. So after cancel out we get limit s tends to 0. After taking limit s tends to 0, we get minus k cube upon k square. This is equal to minus k. So fx at point 0 comma k is equal to minus k. So to compute fxy at point 0 comma 0, we will put these two values in this formula. We get limit k tends to 0. Here we will use minus k and minus 0 upon k, and this gives us value minus 1. Similarly, we can find fyx at point 0 comma 0, and this will be equal del upon del x of f of y at point 0 comma 0, and this value will be equal to limit h tends to 0 f of y at point, this will be 0 comma 0 plus h, that is h comma 0 minus f of y at point 0 comma 0 upon k. So again we need these two values, fy at point h comma 0 and fy at point 0 comma 0. So first of all we will find f y at point 0 comma 0, that is partial derivative of f with respect to y, and it is calculated by this formula k tends to 0 f 0 comma 0 minus 0 comma k minus f 0 comma 0 upon k. So this gives us value 0 minus 0 upon k, that is 0. Now again we will compute fy at point h comma 0, and it will be equal to limit k tends to 0 f here h comma k minus f h comma 0 upon k, and again in place of x we will put h, and in place of k we will use, in place of y we will use small k. So it becomes hk into h square minus k square upon h square plus k square minus 0 upon k. Now taking from here k is cancelled out by k, and taking limit k tends to 0, we obtained here h square into h is h cube, and upon here h square, and we can cancel out it, we get only h. So fy at point h comma 0 is h, and fy at point 0 comma 0 is 0. Now we will use these two values in the above equation, in this equation, and we and we get here is f y h comma 0 is h, and this is not k, this is h, sorry, this is h, this is h minus 0 upon h, and limit s tends to 0. So this gives us value 1. So here we can see that the partial derivative of f with respect to y and x, the value is at point 0 comma 0 is 1, but the partial derivative of f at a point 0 comma 0 with respect to x y is minus 1. So from here we conclude that this implies that f of x y at point 0 comma 0 is not equal to fy comma x. That means the mixed kind derivative of function of two variables at the given point may not be equal. So we need an additional condition on mapping f, and this additional condition is obtained by Euler theorem. And this theorem says that if fxy and its partial derivative that is fx, fy, fxy and fyx all are defined in an open neighborhood of a point a comma b, and all are continuous at point a comma b, then the mixed kind partial derivative of function fxy at point a comma b is equal to fyx at point a comma b. So in this way we can conclude that the partial order derivative of function all are continuous, and function is itself continuous at point a comma b, then its mixed kind partial derivative values both are equal. So thank you very much.